Hey everyone, Big Mac here. So today I'm starting QualQuest again. Um, like I mentioned in the previous video, I worked on a couple practice problems and I figured I would try and do some, just trying to give like an explanation on how these problems work. So, that way you can learn a little bit and I can hopefully understand things a little bit more if I can explain them, so we'll see if that works. Okay. Are you? Yeah. Okay. Seems we're going fine. Okay. So, um, what I'm gonna do is I'm just gonna periodically put up. I'll write everything myself, and then I'll just like randomly take. I'll re-record once I've written everything, because you don't want to see my back, just writing stuff on the board the whole time. So that would not be good for anybody. So, all right. So I will set up the first problem right now. Okay, so here's our first problem that we're going to tackle. It was number 3 on day 1 of our practice test. Basically, we have a weird equation up here. Hopefully you can follow it along, obviously. So we have derivative times an unknown function of another derivative with respect to a function u, and we want to solve that equal to some source term f of x. This kind of equation is usually used in things like the propagation of a temperature through a certain medium like a rod or a stick or something. So we have a couple of conditions here. We have an x is between 0 and 1, and we also have that it is the value of x at 0 is 0, and the derivative of u at 1 is also 0. So if we're going to graph this solution, so this would be x, this would be u. Hopefully you guys will be able to see everything, so it might be a little small, but we know that it's going to start off at 0, and then we expect it to somewhere around x equal 1 to just kind of flatten out. So that's a kind of a graph that we're expecting to look for. Obviously, put this in full screen mode, and I'll try and keep it in a higher quality too when I publish it. So that's the kind of function we're looking at. We want to find the Green's function which is here g as a function of s and z. Actually, if we have a Green's function, then we can actually use it to solve for our original function u in terms of the Green's function f and our source term f, which is the same as up here. So let's get to that. Okay, so basically a brief introduction on Green's functions. Basically, if you plug in a Green's function into where u was originally, you get something really useful. So we have this same equation as before. It's a little different now, though. So instead of u here, we have our Green's function g, and instead of f of x, we have this weird thing called the delta function, where basically it equals this function here. If at every point besides x equals z, it's 0, and it just happens to be infinite at that exact point z. So you can think of it as like an impulse type thing. The other important thing is that it satisfies the same boundary conditions as our original function. So here we have g of 0 is 0 and g prime of 1 is 0. And there will be a couple of other conditions that we'll have to satisfy, and we'll talk about those as we get to them. Alright, so doing a little bit of work, what we know is that since we had our delta function, for all values of x not equal to z, then we just have that our system solves to 0. So since we have a basic derivative here, we can integrate both sides, we pull out a constant, and then this k of x function, we don't know what it is. We do know that it's positive. I actually forgot to mention that. K of x is greater than 0 for all x in that 0 to 1 range. So we can divide both sides by k of x. We have just dg dx, and then to find just g by itself, we integrate both sides, and we have the integral of c over k of x plus another arbitrary constant d. And actually, c and d can often be functions of our function z, because we don't know where z is. All we know is that z is somewhere in between 0 and 1. So at this point z, that is where we're going to have our big discontinuity, where we're going to have our delta function jump. So we have to treat that part a little more carefully, and that's where we have to come in to our other terms about continuity and our jump condition. Alright, so it actually turns out that our point z, which we don't know where in between 0 and 1 it is, but we actually have two separate functions here. And this is how it always is with the Green's function. So like we took our general form from before, I changed the variables around a little bit because we have two conditions. We have one where x is less than z and one where x is greater than z. So I'm going to call where x is less than z, I'm going to call this Green's function g minus, and obviously the other one as g plus. So Green's functions usually have two specific conditions that we also need to apply to besides the boundary conditions. The first one here is known as the jump discontinuity, where basically since we're going to have some kind of discontinuous, or not discontinuous, the function itself, the Green's function itself is going to be continuous, but we're going to have like it's not going to be differentiable at the point x equals z. So therefore we have this special condition where, if we take the limit of g plus as we approach z from the positive side, minus the limit of g minus as we approach z from the minus side, it turns out that this difference is equal to 1 over k of x, because it turns out that k of x is known as our Sturm-Liouville component in this equation. So another thing is that you need functions to be in Sturm-Liouville form in order to be able to solve them using Green's functions. So it turns out that this is our k of x from earlier. And then the other thing I mentioned is that our Green's function does have to be continuous at the point z. So it's got to be the same, from both directions. So looking at a graph, again, here's 0, here's 1, here's our z somewhere in the function. So we're going to have our function do something weird. I mean, it might not actually, might not be smooth or something, but, it's going to have some bizarre behavior at that point z. So obviously the derivative does not exist because it's different from both sides. Alright, so plugging our Green's function into our initial boundary conditions. Remember we had said that g of 0 had to be the same as u of 0, so that's 0, and g prime of 1 has to follow u prime of 1 to also be 0. So since we know that our z function is somewhere in between 0 and 1 and not at those endpoints, we know that g of 0 has to apply to our function g minus, and g1 prime has to apply to our function g plus. So plugging in these into our terms, so evaluating g minus at 0, the integral goes away because if you integrate, between 0 and 0, you get absolutely nothing out of it. So then you're left with b, which has to be 0. Secondly, if we go to g plus and evaluate our derivative at x equals 1, all we have left is c over k of 1, and which equals 0, and like we mentioned earlier that k is a positive function, therefore the only possibility is that c coefficient is 0. Thus we've simplified our equation a little bit. So we have this integral from x is less than z, and we know that it's just some constant after x is equal to z. So okay, we're getting close to being done here. So we had our two other conditions besides our boundary conditions, which I mentioned were the jump and the continuity conditions. So using our jump condition up here, we had our differences of our slopes, and we said that was 1 over k of c because of the Sturm-Liouville condition. Since g plus was a constant, its derivative is just 0, and g minus we just have a over k of c, or k of z. So obviously from this point we see that a has to be negative 1, so then this becomes our function for g minus, just as it is. We have a negative integral from 0 to x of 1 over k of x dx. The other condition we had was our continuity, which said that at the point z, our g minus and our g plus had to be the same. So then therefore, plugging in z for our lead variable x, we have d that becomes the negative integral from 0 to z of 1 over k of x dx. And obviously here, this whole x being inside thing is just a dummy variable at this point. I probably could have used x prime just to differentiate between, which is the, just between the variables. But I mean, this basically becomes the evaluation as a function. So we're all good. And thus, this is our resulting Green's function. Alright, so this was number 3 of our QualQuest venture for today. I'll probably just do one problem because I didn't realize how much time this was going to end up taking. So I'll probably just do one problem per week or maybe 2, but usually in this format since, most of these problems take a little bit of setup and explanation. Alright, this is Big Mac saying later.